Welcome to the Curious Voyager. It's lovely to have you here tonight. Wherever you are right now, tucked under a blanket with the lamp turned low, or lying flat in the dark with your eyes already half closed, or somewhere on a late train with the window cool against your cheek, I'm glad you found your way here. Settle in. There's no hurry tonight. None at all. We're going to move slowly the way you'd wander through a quiet museum after closing time, with no one rushing you along and nowhere you need to be. And before we begin, I'd love to know, where in the world are you listening from tonight? What time is it in your corner of the world? Whether it's late evening or the deep middle of the night, whether it's raining outside or perfectly still, leave a little note if the mood takes you. I always find it strange and wonderful, the thought of all these different rooms, all these different hours, all of us drifting toward the same quiet place. If you enjoy these slow journeys, and you'd like more nights like this one, a gentle like and a subscribe really do help this sleepy little channel keep going. Small creators like me lean on that more than you'd think. And to those of you who've already subscribed, truly, thank you. You're the reason there's a next one. Now, here's my one small promise for the night. I'm going to try very hard not to make this so interesting that it keeps you awake. I'll probably fail a little because the thing we're going to talk about is one of the strangest and most beautiful ideas in all of modern physics. But if it does keep you awake, well, at least you'll have learned something lovely along the way. A fair trade, I think. And if you drift off long before the end, that's perfectly fine. That's the whole point. The ideas will still be here when you wake. You don't need to follow every step. You don't need to understand all of it. You just need to let the words carry you like a current somewhere soft. So, let's begin, shall we? Imagine for a moment that you're holding an ordinary crystal of salt. Just a single grain, the kind that might fall from the rim of a glass and land on a wooden table. Too small to really see, but real and solid and old in its own quiet way. If you could shrink yourself down, as smaller than dust, smaller than a speck of dust on a speck of dust, until you were standing among the atoms of that grain of salt, you would see something astonishing. You'd see order, perfect, patient order. The atoms wouldn't be scattered about like crumbs. They'd be arranged in a neat, repeating pattern, a lattice, a kind of three-dimensional scaffolding that goes on, the same shape repeating over and over, marching off in every direction. Sodium, chlorine, spaced out at exactly the same distance, again and again and again, like tiles on an endless bathroom floor. That repetition, that's the secret of a crystal. That's what makes a crystal a crystal. It's not the hardness, not the sparkle, it's the repeating, a pattern in space that copies itself over and over, perfectly spaced. Now hold that picture in your mind, the salt, the endless repeating lattice, the pattern that stretches out across space. And here is the question I want to plant in you tonight. The question this whole journey grows from. It's a small question. It sounds almost like something a curious child might ask, half asleep, staring at the ceiling. The question is this. A crystal repeats itself across space. So, could something repeat itself across time? Sit with that for a second. We know patterns can repeat in space, and that's just an ordinary crystal, nothing exotic. You've got them in your salt shaker and your window panes and the diamond on someone's hand. But time is different, isn't it? Time only goes one way. Time flows. Could there be a kind of matter that instead of repeating its pattern across the room, repeats its pattern across the hours? A thing that returns again and again to exactly where it started. Not in space, but in time. A clock made not of gears, but of matter itself ticking. That's what a time crystal is. And tonight, slowly, gently, we're going to find out how on Earth such a thing could be real. Because it is real. It's been built. It's been built inside a chip in a laboratory, and it does something that sounds, at first, completely impossible. Let me give you the picture that makes it click. The image I want you to carry with you, soft, into sleep. Picture this strange crystal. Now imagine you give it a little nudge, a poke, once every second. Tick. You poke it, you wait a second, you poke it again. Steady, regular, like a metronome. Tick, tick, tick. You'd expect it to respond in the same rhythm, wouldn't you? You poke once a second, so it should wiggle once a second. That's how almost everything in the world works. Push a swing once a second, and it swings once a second. But this crystal doesn't do that. You poke it every second, and it answers back only every 2 seconds. Tick, and nothing. Tick, and there it is. Tick, and nothing. Tick, and there it is again. It takes your fast, steady rhythm and it responds with a slower, steadier one of its own, exactly half the speed, perfectly, over and over. You're tapping out a beat, and it's dancing to a beat twice as slow, and it never loses count. Just keeps answering every 2 seconds, with a patience that's almost eerie. That doubling, and that's the heartbeat of the whole story. Physicists have a name for it, a slightly clumsy name, and I'll give it to you so you have it, but don't worry about holding on to it. They call it a subharmonic response. Subharmonic, meaning a rhythm underneath the rhythm you'd expect, a slower beat hiding beneath the one you're providing. You drive it at one speed, it lives at half that speed, and the system has, in a very real sense, chosen its own rhythm, one that doesn't match the rhythm of the world poking at it. It has broken the time symmetry of the situation. It's marching to its own clock.
And the truly strange part, the part the headlines love to shout about, is that this dance can, in the ideal, go on forever. Without winding down, without burning up any usable energy. A crystal that ticks and ticks and ticks, seemingly without ever paying for it.
Now when you hear that, a thing that moves forever without burning energy, a little alarm probably goes off somewhere in the back of your mind. That sounds like perpetual motion. That sounds like the one thing everyone's always told you is impossible. A machine that runs forever, free for nothing. The dream of cranks and dreamers for centuries, the thing physics swears up and down, can never ever exist. Hold on to that suspicion, keep it close, because it's the right instinct, and untangling it is going to be the most beautiful part of our whole journey tonight. The answer is far stranger and far lovelier than either the breathless headlines or the flat denials. Nature, it turns out, found a kind of loophole, a way to have eternal motion without breaking a single law. But we'll get there slowly. No rush. We have all night. Let me first show you why this idea is even surprising in the first place, because to feel the wonder properly, you have to feel how it cuts against everything you already know about clocks. Think about a watch, an ordinary quartz watch, the kind that might be on your wrist or your nightstand. There is, in fact, a crystal inside it, a tiny sliver of quartz cut very precisely, shaped a little like a tuning fork smaller than a grain of rice. And that crystal vibrates. It shivers back and forth at an astonishingly steady rate. That's how your watch keeps time so well. The quartz crystal trembles, the watch counts the trembles, and from that counting it knows the seconds. But, and this is the whole point, the quartz crystal only trembles because something is pushing it. There's a battery. A little electric pulse goes into the crystal and makes it flex, and that flex is what keeps it shivering. The moment that battery dies, the crystal goes still. The shivering stops. The watch stops. The crystal, on its own, with no energy fed in, does absolutely nothing. It just sits there, silent, inert, like every other ordinary object in the world. Stillness is what matter does when you stop feeding it energy. Everything winds down, everything comes to rest. That's the deepest, most familiar rule of the physical world. Leave something alone, take away its fuel, and eventually it stops. The pendulum slows, the spinning top topples, the hot tea goes cold, things settle. So when someone tells you they've found a crystal that keeps ticking, that returns to its rhythm again and again, forever, in its lowest and laziest state, without consuming any usable energy to do it, they are describing something that seems to laugh in the face of that rule, a crystal that doesn't need a battery to keep its rhythm, a clock that ticks for free. That's the startling claim. That's why, without burning any energy, stops you in your tracks. Now you can feel why physicists, when they first heard the idea, were so unsettled by it, and why some of them, as we'll see, were absolutely certain it could not be done. But before we meet those physicists, I want to give you the deeper idea underneath all of this. The one beautiful concept that ties the salt crystal and the time crystal together. It's a phrase that sounds grand, but the idea behind it is gentle. And once you see it, you start seeing it everywhere. The phrase is spontaneous symmetry breaking. Let me unwrap it slowly because it really is the key to the whole night, and there's no need to grasp it all at once. Let it wash over you. Start with the word symmetry. In everyday life, we think of symmetry as a face that matches left and right, or a snowflake, or a butterfly's wings. But to a physicist, symmetry means something a little broader and a little quieter. It means sameness under change. It means you do something to a system and afterward it looks exactly the same as before, as if nothing happened. Here's the gentlest example I can give you. Imagine empty space, just space, nothing in it, perfectly smooth and featureless in every direction. Now imagine you took a tiny step to the left. One step, look around. Has anything changed? No. Empty space looks exactly the same wherever you stand in it. Take another step or 1,000 steps. Same emptiness, same everything. There's no special spot, no landmark, no here that's different from there. That sameness, that it doesn't matter where you are, it all looks the same, is a kind of symmetry. Physicists call it continuous spatial translation symmetry, which is a mouthful, but all it means is this. You can slide along smoothly by any amount in space, and nothing changes. Smooth, featureless, the same everywhere. Now, watch what happens when a crystal forms. You take a liquid, say salty water, with the sodium and chlorine atoms floating about freely, drifting wherever they please. In that liquid, every spot is as good as any other. The atoms have that lovely smooth symmetry. They could be anywhere, and it would look the same. There's no preferred place to be. But then you let it cool, you let it dry, and as it does, something happens. The atoms stop drifting, they settle, they lock into that neat, repeating lattice we talked about. Sodium, chlorine, each at its own fixed spot, spaced exactly the same distance apart. And here's the crucial thing. Now there are special places. There's a place where an atom sits, and a place in between where no atom sits. The smooth, anywhere is fine sameness is gone. The crystal has picked out specific spots and ignored the rest. It has chosen. That's the breaking part. The crystal took a smooth situation where every position was equal, and it broke that equality. It settled into a pattern that's only the same if you slide it by exactly the right distance. One lattice step, instead of any distance at all. The perfect smooth symmetry got broken down into a smaller, choppier, repeating one, and the word spontaneous. That just means nobody chose for it. No outside hand came in and said, put your atoms here. The system did it all by itself, simply by cooling down and settling into its most comfortable, lowest energy arrangement. The order appeared on its own, out of the smoothness, spontaneous symmetry breaking, smoothness becoming pattern all by itself. You see this everywhere, once you know to look. Take a magnet. Heat a piece of iron up red hot, and inside it all the tiny atomic magnets are pointing every which way, jumbled, no direction preferred over any other. Beautifully symmetric, no up, no north. But let it cool, and below a certain temperature, something tips. All those little atomic magnets suddenly agree. They all swing to point the same way, and now there is a north. There is a direction the iron has chosen. The smooth, all directions are equal symmetry has broken spontaneously into we all point this way. That's why a magnet is magnetic. It's the same deep story as the salt. Smoothness settling, all on its own, into a pattern that picks one option and breaks the perfect sameness. So that's the idea. A crystal is what happens when matter spontaneously breaks the smooth symmetry of space, when atoms that could have sat anywhere instead choose to repeat themselves at fixed spots, marching across the room in a regular pattern. And now finally you can feel the full shape of the question, the childlike question I planted at the start. Because if matter can spontaneously break the symmetry of space, if it can take smooth, featureless space and carve it into a repeating pattern all by itself, then why not time? Why couldn't matter take smooth, featureless time, where every moment is as good as any other, and break it all by itself into a repeating pattern of moments? A pattern that returns tick-tick at regular intervals, not across the room, but across the hours. A crystal in time, settling into a rhythm the way a salt crystal settles into a lattice. It's such a clean, such an obvious-sounding question once you've seen the pieces. Crystals repeat in space. Why couldn't something repeat in time? And the wonderful thing, the very human thing, is that for the longest time, nobody asked it. It seems so natural now, laid out gently like this in the dark. But the parade of brilliant physicists who spent a century studying crystals and magnets and symmetry breaking, who knew all of these pieces intimately, somehow walked right past this particular door for decades. Sometimes the simplest questions are the ones nobody thinks to ask out loud. They feel almost too naive, too childlike. Surely, if it were possible, someone would have noticed by now. And then in 2012, someone did ask it out loud, and not just anyone. His name is Frank Wilczek, and he is, by any measure, one of the great physicists of our age. In 2004, he was awarded the Nobel Prize in Physics, the highest honor the field can give, for work he'd done decades earlier as a very young man on something called asymptotic freedom. I won't take you deep into that tonight. It belongs to a different story. But let me give you just the gentle shape of it so you know the caliber of the mind we're dealing with. Asymptotic freedom is a strange and lovely fact about the strong force, the force that glues together the insides of every atom's nucleus, the force that holds the very heart of matter together. Wilczek, along with his collaborators, worked out something deeply counterintuitive about how that force behaves. Most forces get weaker as things move apart and stronger as they come close. The strong force does something almost backward. In certain ways, it gets weaker as the particles it binds are squeezed closer together and fiercer as they try to pull apart, like a bond that grips harder the more you struggle against it. Working that out reshaped our understanding of what holds matter together at the smallest scale, and it won him the Nobel. He's a professor at MIT, one of those rare minds equally at home in the deepest mathematics and in big, playful, wandering questions about the universe. And it was one of those big, playful, wandering questions that he turned to in 2012. He'd been thinking, by his own account, about crystals and about superconductors and about all the ways matter spontaneously organizes itself by breaking symmetry. And the childlike question floated up. Crystals break the symmetry of space. Why not time? Why couldn't there be a phase of matter that breaks the symmetry of time, that in its lowest energy state, its most settled and natural state, spontaneously starts to tick, not driven by a battery, not pushed by anything, but ticking simply because that's what its most comfortable state does, the way a salt crystal repeats in space simply because that's what its most comfortable state does. He found the question so striking that he gave it a name, and the name itself is a little stroke of poetry. He called it a time crystal. A crystal, but in time instead of space. And in 2012, he wrote it up properly in the language of mathematics and physics and published it in one of the most respected journals in all of physics, a journal called Physical Review Letters, Volume 109, if you like to keep the details. Article number Wagstein 0401, he titled it, simply and boldly, Quantum Time Crystals. Alongside it ran a companion paper he'd written with a colleague named Alfred Schapper, exploring a related, more classical version of the same idea, that one published right beside it, Article 160402, the very next number, the two papers sitting side by side like twins. And with that, the idea was out in the world. A Nobel laureate had stood up and said, in effect, I think matter might be able to crystallize in time. I think there could be a state of matter that ticks forever in its ground state, that breaks the symmetry of time the way salt breaks the symmetry of space. Now you might imagine that when a freshly minted Nobel laureate proposes a beautiful new idea, the world simply nods and accepts it. But that's not how physics works, and thank goodness for that. Physics is a stubborn, skeptical, argumentative discipline, and the higher the reputation of the person making the claim, the harder everyone else pokes at it, looking for the flaw. A beautiful idea earns no special protection. If anything, it draws more scrutiny, not less. That's the strength of the whole enterprise. Nobody's name is big enough to make a wrong idea right. And Wilczek's idea, this lovely crystal in time, was about to be poked very hard indeed, because there was a problem hiding inside it, a deep one. Within just a few short years, other physicists, careful, brilliant ones, would take Wilczek's proposal in its original form and prove, with the cold certainty of mathematics, that it simply could not exist. Not probably doesn't, not we haven't found one yet, but in its original form, proven flatly, mathematically, impossible. And yet, here we are tonight with a time crystal having been built, ticking inside a real machine, in a real laboratory. So both of those things are somehow true. The idea was proven impossible and the thing was built anyway. How can that be? How do you get from mathematically forbidden to running on a chip? What was the trick, the loophole, the sideways escape that brought a dead idea back to life? That's exactly where we're heading, but not tonight in a rush. Let it sit with you for now, that gentle paradox. Proven impossible, and yet built. Two things that can't both be true, and somehow are. There's a way through, and it's one of the most elegant escapes in modern physics, and we'll walk through it slowly, step by gentle step. For now, just let the picture settle in your mind, the way the atoms settle into the salt. A crystal that repeats not in space but in time. A clock made of matter ticking to its own slow rhythm. Poke it every second, and it answers every two. A Nobel laureate's childlike question written down in 2012. And waiting just ahead of us, the strange and lovely contradiction we'll untangle together. The idea that died and came back.
Rest here a moment. There's no rush at all. We've only just begun, and the night is long. And the strangest, most beautiful part is still to come. Let me hold that picture a little longer because it's worth holding. Think of ordinary table salt for a moment. The stuff sitting in a shaker somewhere in your kitchen right now. If you could shrink down small enough to walk inside a single grain, you'd find something astonishingly orderly.
Sodium and chlorine atoms locked together in a perfect repeating grid, row after row after row, each one spaced exactly the same distance from the next, up, down, left, right. The same pattern, over and over, marching off in every direction. The atoms could, in principle, have settled anywhere at all. Space doesn't care where they sit. And yet they chose this, a fixed, repeating lattice. They picked a pattern out of a sea of possibilities. That's the thing to keep close tonight. A crystal is matter that repeats itself across space. And what Wilczek wondered, the question that started all of this, was whether matter could do the very same thing, but across time instead. Not a pattern that repeats as you move from here to there, but a pattern that repeats as the seconds tick by. Something that returns to the same arrangement again and again at regular intervals, all on its own. A crystal you don't see by looking sideways across a grain of salt, but one you'd see by watching the same spot and waiting and watching it come back around. And before we go any further, let me say a quiet thank you for being here. If you find these slow journeys soothing, a gentle like and a subscribe really do help this little channel keep going. Small creators like me lean on that more than you'd think. And to anyone already subscribed, settling in again tonight, thank you truly. It means a great deal. So before we drift on, tell me, where in the world are you listening from tonight? What's the hour where you are? Is the sky already dark or just beginning to soften? Picture it for a moment wherever you are. The lamp still glowing low, the blanket pulled up, the day finally letting go of you. There's nothing you need to hold on to here. If you drift off somewhere in the middle, that's perfectly all right. The ideas will still be here, waiting, patient as the stars. We'll move slowly, softly, one small mystery at a time, and you don't have to grasp every piece. You just have to let it wash over you. Now let's go back to that question, because there's something hiding inside it that should stop us in our tracks. Think about the clocks you've owned. Nearly every one of them, somewhere in its quiet heart, has a tiny sliver of quartz. Quartz is itself a crystal, atoms of silicon and oxygen repeating in space just like the salt. And quartz has a lovely property. When you run a little electricity through it, it vibrates ever so slightly at a very precise rhythm. That steady shiver is what keeps the time. It's why the watch on your wrist or the clock on the wall keeps such faithful pace. But here's the part we tend to forget. That quartz needs the battery. Take the battery out, and the shivering stops. The crystal goes still and silent. It vibrates only because something is feeding it energy, drip by drip, second by second. Every clock you've ever owned has needed that constant little push from somewhere. You'd wind it, plug it in, slip a battery inside. Nothing keeps time for free. And that's precisely what makes Wilczek's question so startling. He wasn't imagining a better quartz watch. He was imagining a crystal that returns to the same state over and over in time, in its own lowest, calmest, most settled state. A rhythm that belongs to the matter itself. Not a shiver borrowed from a battery, but a beat that's simply part of what the thing is. A clock made of matter, ticking to its own slow pulse without anyone winding it up. Sit with how strange that is, even just for a breath. We're so used to the rule that motion costs something, that to keep a thing moving you have to keep paying for it. And here is a question asking, what if some special arrangement of matter could keep its rhythm without that price? It sounds, at first, almost like cheating. We'll come back to whether it really is. For now, just feel the oddness of it. To understand what Wilczek was really reaching for, we need one beautiful idea, and it has a slightly grand name: spontaneous symmetry breaking. Don't let the name worry you. It's gentler than it sounds, and once you see it, you'll start noticing it everywhere. Let's go back to the salt for a moment. Before those atoms settled into their grid, imagine them as a kind of formless possibility, free to sit anywhere, with no spot more special than any other. In that state, space itself looks perfectly even. Slide everything an inch to the left and nothing would look different, because nothing has chosen a position yet. That perfect evenness, where every place is as good as every other, is what a physicist would call a symmetry. Continuous translation symmetry in the language of the field. Well, it's a fancy way of saying smooth and the same everywhere you go, but a crystal can't keep that perfect evenness. When the atoms lock into their lattice, they have to choose. They pick particular spots with particular spacing, and suddenly space is no longer the same everywhere. Now there are atoms here and gaps there in a fixed rhythm. The smooth, anywhere is fine evenness gets broken and replaced by a pattern. That's the breaking of symmetry, and it's spontaneous because nothing from outside told the atoms exactly where to go. They settled into their pattern all on their own, the way water, cooling, decides without instruction to become ice. You see the same quiet magic in a magnet. Inside a piece of iron, you can picture countless tiny compass needles, one for each atom, each able to point any direction it likes. When the iron is hot, they all point every which way, a jumble with no preference. Perfectly even, perfectly symmetric, no direction more special than another. But cool it down and something lovely happens. All those tiny needles, with no outside hand arranging them, suddenly agree. They line up, all pointing the same way. And just like that, one direction has become special. The evenness is broken. A pattern has appeared out of sameness, chosen by the matter itself. That's a magnet being born, and it's the very same kind of spontaneous symmetry breaking that gives us salt and diamond and quartz. So this idea of matter, spontaneously choosing a pattern, of breaking a smooth evenness in space, is the language Wilczek was working in. Crystals break the evenness of space. Magnets break the evenness of direction. And he looked at all of it and asked the simplest, most childlike question of all. Why only in space? Why not in time? It's worth pausing on the man asking it because it tells you this wasn't idle daydreaming. Frank Wilczek is not a physicist on the fringes. He's a Nobel laureate. He shared the Nobel Prize in Physics in 2004 for work on something called asymptotic freedom, a deep piece of the theory that describes the strong force, the force that binds together the very hearts of atoms. He works at MIT, among the sharpest minds in the field. This is someone who has spent a lifetime in the deepest waters of physics. And yet the question he asked here is one a curious child might ask. Things repeat in space. Why couldn't something repeat all on its own in time? There's a real beauty in that, I think. That sometimes the most profound questions are the simplest ones, the ones we usually forget to ask, because the answer seems too obvious to bother with. Of course, things don't tick forever on their own, we'd say. Everything winds down, everything needs feeding. But Wilczek didn't take the obvious for granted. He pulled at the thread, and in 2012, he wrote the idea down. The paper appeared in a journal called Physical Review Letters, Volume 109, the article numbered 160401, if you ever care to look. He gave the idea a name that's stuck ever since, a name with a lovely strangeness to it, a quantum time crystal, a crystal not of space but of time. He wasn't quite alone in it either. Alongside that paper came a companion, written with a colleague named Alfred Schapere. The very next article in the same journal, numbered 160402, where Wilczek's paper reached toward the quantum world of the very small, the Schapere-Wilczek paper explored the idea in the ordinary, larger world of everyday physics, what they called a classical time crystal. Two papers side by side, opening the same strange door from two directions at once. And that's where the trouble began. Because no sooner had this lovely, childlike question been written down and given its name, than the rest of the physics world turned to look at it. And what they found when they brought the full weight of their mathematics to bear was not encouragement. What they found was a proof, not a suspicion, not a concern, not a raised eyebrow across a seminar table, a proof, the kind that closes doors. The first arrived from a physicist named Patrick Bruno in 2013, less than a year after Wilczek's papers had appeared. Bruno sat down with the mathematics of the proposal, the actual quantum mechanics of a system trying to settle into its lowest energy state, its ground state, while also perpetually oscillating. And he worked through it carefully. And what came out the other end of that careful work was not a time crystal. It was a demonstration that a time crystal, in the way Wilczek had originally imagined it, simply could not exist. The argument, put plainly, goes something like this. Imagine you have a system, a collection of particles, say, sitting quietly in its ground state. The ground state is the lowest rung of the energy ladder. There is no lower place to fall. The system isn't moving anywhere. It isn't doing anything. It has settled as completely as anything in the universe ever settles. Now, Wilczek had asked whether such a system could nonetheless spontaneously organize itself to oscillate, to tick, periodically, all on its own, like a clock winding itself for free. Bruno's mathematics said no. A ground state, a true quantum ground state, has a definite, fixed energy. And a system oscillating in time does not have a definite, fixed energy. The two descriptions are incompatible. You cannot build a perpetually ticking thing out of a perfectly resting foundation. It's a little like asking whether a ball sitting at the very bottom of a perfectly smooth bowl, not rolling, not wobbling, just resting at the lowest possible point, could nonetheless be spontaneously rolling around the rim. You can't have both at once. The math simply refuses. Bruno published his finding in Physical Review Letters, the same journal where Wilczek's papers had appeared, and the physics community read it with the slow recognition of a door being shut, gently but firmly. But that was not quite the end of the story, because in science, one proof of impossibility is sometimes the beginning of a more careful question. And two other physicists were, around the same time and in the years that followed, working toward a far more general closing of the door. Their names are Haruki Watanabe and Masaki Oshikawa, and in 2015 they published a paper in Physical Review Letters, Volume 114, Article 251603, that went considerably further than Bruno's result. Where Bruno had shown that Wilczek's specific construction didn't work, Watanabe and Oshikawa showed something broader, something more fundamental. They proved with the generality that mathematicians dream of that no system sitting in true thermal equilibrium, no matter how cleverly constructed, no matter what materials or interactions you chose, could spontaneously break continuous time translation symmetry. That phrase deserves a moment. A continuous time translation symmetry is the technical way of saying something you've known your whole life without needing a name for it. The laws of physics don't care what time it is. If you set up an experiment on a Tuesday, it will give the same results on a Thursday. The universe doesn't run differently at 3 in the afternoon than it does at midnight. Time keeps flowing and the rules stay the same. That sameness, that invariance, is what physicists call time translation symmetry. It's one of the deep, quiet symmetries woven into the fabric of physics. Wilczek had imagined that a time crystal would break that symmetry spontaneously. A system that ticks every second, say, has picked a particular rhythm. It is no longer the same at every moment, but instead different at half seconds and full seconds, returning to itself only after a complete cycle. That's a broken symmetry. It has chosen a pattern in time, just as an ordinary crystal chooses a pattern in space. What Watanabe and Oshikawa proved was that in thermal equilibrium, in any system that has had time to settle into contact with its environment and reach a steady, unchanging state, this kind of spontaneous time ordering simply cannot occur. Equilibrium is too settled, too featureless. In equilibrium, the whole idea of a system being genuinely different from moment to moment, while still being in its lowest energy state, turns out to be self-contradictory. The math is unsparing about it. So there it was. By 2015, 3 years after the beautiful question had been asked, the answer seemed to be impossible. Not merely difficult, not merely a challenge for better engineers. Impossible in the same way that a triangle with 4 corners is impossible, in the same way that a ball rolling uphill forever in an empty room is impossible. The logic of thermal equilibrium and the logic of quantum ground states simply would not permit it. And yet, here is the part of the story where science does something that it does so rarely that it still feels every time like a minor miracle. It looks at the proof and says, yes, correct. You've proved exactly what you claimed to prove. Now watch what happens when we move outside the place where your proof applies. Because Watanabe and Oshikawa's theorem and Bruno's before it applied to systems in thermal equilibrium. Systems that have settled, systems that have reached a resting state, that have had all the interesting energy differences ironed out by contact with a heat bath, by time, by the slow leveling that thermodynamics enforces. The proofs were watertight. They just weren't proofs about everything. They weren't proofs about what happens when you never let a system settle. This is the rescue. And it came from several directions at once, in 2015 and 2016, in a flurry of theoretical papers that physicists would later look back on as one of those rare moments when an entire field pivots on a hinge. The first pivot point was a physicist named Christoph Sacher. Working in 2015, publishing in Physical Review A, Volume 91, Article 033617, Sacher explored the possibility of time crystal-like behavior, not in a system sitting quietly in equilibrium, but in a system that was being driven, periodically nudged, poked at regular intervals by an external force. A system that was, in the language of the field, out of equilibrium. Sacher found that in this driven setting, behavior that looked very much like the time Frank Wilczek had dreamed of could indeed emerge. The door that had been closed to equilibrium systems was perhaps still open a crack for driven ones. And then, in 2016, the crack became a doorway. 2 groups of theorists working independently, essentially simultaneously, converged on the same answer from slightly different directions. The first group included Dominic Elser, Bella Bauer, and Chetan Nayak. Their paper appeared in Physical Review Letters, Volume 117, Article 090402. The second group included Vedika Khemani, Achilles Lazaridis, Roderick Mersner, and Shivaji Sondhi, publishing in Physical Review Letters as well. Volume 116, Article 2541. These are not names you'll likely have encountered before unless you read theoretical condensed matter physics journals over breakfast. But what they worked out between them is the central idea that makes everything else in this story possible. They formalized with precision and rigor the concept of the discrete time crystal. And to understand what that is, really understand it, not just the name, you need to spend a little time with a concept called a Floquet drive. Don't let the name put you off. The underlying idea is almost cozy in its simplicity. Imagine you have a system, let's keep it abstract for now, a collection of interacting particles, a ring of them, say, and instead of letting it sit in peace, you poke it. Periodically, at perfectly regular intervals, you apply a pulse, a shake, a nudge. The period between nudges, the time from one poke to the next, is given the name t. You poke it at time 0, then at time t, then at time 2t, then at 3t, and so on, forever in the idealized version. Evenly spaced, rhythmic, like a very patient and very precise finger tapping on a table. This kind of periodic driving is what physicists call a Floquet drive, named after a 19th century French mathematician named Gaston Floquet, who worked out the mathematics of periodic systems long before quantum mechanics or time crystals were even imaginable concepts. So when physicists say a system is Floquet-driven, they mean exactly this. It is being pushed periodically with a rhythm by something external to it. Now here is the first thing you might expect thinking about it from ordinary intuition. If you poke something periodically, it will most likely respond periodically, with the same period. You tap a drum every second, and the drum sounds every second. Simple enough. The response matches the drive. But here is the startling thing, and the thing that is at the heart of what Elsa and Nyack and Kamani and their colleagues found. A discrete time crystal does something different. Something that, when you first hear it, sounds almost like the system is being slightly cheeky. You poke it once every second, and it answers every 2 seconds. Not once a second, twice as slow. A response whose period is twice the period of the drive. The physicists call this a subharmonic response, or, more evocatively, period doubling. The system, when it responds at all, responds at half the frequency you drove it with. You give it a rhythm, and it stubbornly, persistently returns to itself only on every other beat. This is the broken symmetry made concrete. The drive has a period of t. A system that responded normally, that simply did what it was told, would have a period of t as well. The physical state at time t would look the same as the physical state at time 0. But in a discrete time crystal, the state at time t looks different from the state at time 0. The system has only returned to its starting configuration at time 2t, at twice the period. The drive has the symmetry of a 1-beat rhythm. The response has the symmetry of a 2-beat rhythm. Those are different. The symmetry of the drive, with the discrete time translation symmetry of the periodic kicking, has been spontaneously broken by the response of the system itself. This is worth sitting with for a moment if you're still awake enough to sit with it. Imagine you're in a room with a metronome, tick, 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 evenly spaced. If you clapped along, you'd clap to every beat. That would be a normal response to a periodic drive. Your clapping and the metronome share the same rhythm, the same symmetry. But now imagine that the room itself somehow only resonated on every other beat. The walls themselves vibrated at tick, silence, tick, silence, in a 2-beat pattern, even though the metronome was doing tick, 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 without distinction. The room has broken the symmetry. It has chosen a pattern of its own, a pattern that is different from the pattern imposed on it. And that chosen pattern, stable, persistent, spontaneous, is the signature of a discrete time crystal. And here is where you might be raising a question, even half asleep, that the physicists raised immediately. If you're driving this system, if you're putting energy in with every nudge, isn't it just storing up energy, building towards something? Surely a system being continuously poked must eventually do something dramatic with all that input. A pendulum you keep pushing will eventually swing harder and harder. An engine you keep feeding will eventually overheat. Any system receiving energy continuously from outside will, in the long run, heat up. This is, in fact, exactly what happens to most driven quantum systems. This is the nightmare scenario that Floquet physics had to confront even before time crystals became a concern. You drive a quantum system periodically, and in the generic case, over time, it absorbs more and more energy from the drive, its internal states becoming more and more scrambled, until it reaches what physicists call an infinite temperature state. a state of perfect, featureless maximal disorder where every possible configuration of the system is equally probable. This is not a dramatic explosion. It is something almost worse, a slow, inevitable slide into sameness, into a state where no structure remains, where the system has become completely randomized by all the energy it's absorbed. It has, effectively, dissolved. A discrete time crystal, if it simply sat there being driven, should by rights dissolve in exactly this way. Every pulse from the Floquet drive adds a little energy. The system heats up. The beautiful period-doubled oscillation, if it ever existed, gets washed away in the warmth. The clock melts. This is why, for a while, even the driven approach seemed to be in trouble. You'd escaped the equilibrium no-go theorem, but you'd run straight into a different wall: thermal death by driving. And this is where a second key idea enters the story. This is the idea that Elsa, Nyack, Khemani, Mersner, Sondi, and others wove together with the Floquet driving to make the discrete time crystal not just possible but stable. The idea goes by a name that sounds more like a tongue twister than a concept, but it earns your patience. Many-body localization. Take a moment, let the name settle. Many-body localization. It gets abbreviated in the literature as MBL, and it is one of the most surprising phenomena in all of contemporary physics. Here is the basic picture. Imagine a system of many particles, electrons, spins, atoms, qubits, whatever your preferred ingredient is, arranged in some kind of lattice or chain. And imagine that the arrangement is not perfectly regular. There are impurities, defects, random bumps in the landscape. Maybe some sites have slightly different energies than others, scattered without pattern, like a floor with randomly distributed tiny hills and hollows. In a clean, perfectly ordered system, if you disturb one particle, if you give it a little extra energy, that disturbance tends to spread. The energy flows outward, diffuses through the system, and eventually the whole system heats up uniformly. This is normal, this is thermalization, this is, in fact, what the second law of thermodynamics is enforcing. Energy spreads out, disorder increases, everything levels off. But in a system with enough disorder, with enough of those random bumps and hollows in the energy landscape, something extraordinary can happen. The particles can become localized. Their quantum wave functions, the probability clouds that describe where they are and how they behave, can get pinched, trapped, confined to small regions of space rather than spreading freely. And when this happens across an entire many-body system, and when all the particles are localized, not just one, the result is that the system stops thermalizing. Stop and think about what that means. It means that if you put energy into one part of a many-body localized system, that energy doesn't spread, it stays where you put it. The system does not heat up uniformly, it does not reach thermal equilibrium, it does not dissolve. And crucially, the disorder that causes this localization doesn't have to be perfectly engineered. A sufficient degree of randomness combined with interactions between the particles is enough. The many-body localized system is, in a deep sense, self-protecting against thermalization. Now bring the Floquet drive back. You're driving a many-body localized system periodically. Each pulse of the drive tries to add energy to the system, but the localization prevents the energy from being absorbed uniformly. It prevents the system from heating up. On average, over many drive cycles, the system absorbs no net energy from the drive. The potential thermal death, the slide toward the infinite temperature featureless state, is arrested. The crystal doesn't melt, and so the period-doubled oscillation of the time crystal's heartbeat can persist. Because the system is being driven, it is not sitting in an equilibrium ground state, so the Watanabe-Oshikawa no-go theorem doesn't apply. And because the many-body localization is preventing thermalization, the continuous driving doesn't destroy it. The discrete time crystal lives in the gap between those two prohibitions. It threads the needle. This is the rescue. Not a workaround, not a trick, but a genuine new physical phenomenon, a many-body localized, periodically driven system that spontaneously breaks the discrete time translation symmetry of its drive and exhibits a subharmonic, period-doubled response that is stable and, in the theoretical ideal, indefinitely. It is worth saying again, slowly, a system that beats to its own rhythm, different from the rhythm imposed on it, and maintains that rhythm without heating up, without dissolving, without losing its structure. A clock that the physicist has made not by engineering perfect parts, but by making those parts just disordered enough to protect themselves from the chaos the driving would otherwise cause. There is something almost paradoxical in it. The disorder, the very thing that seems like it should make the system worse, messier, less organized, is precisely the ingredient that keeps the order alive. The randomness is the shield. And there is something else, something quieter, that deserves a moment here before the story moves forward. When Elsa, Bauer, and Nyack, and the other group around Kemani and their colleagues put this all together in 2016, they weren't just solving a theoretical puzzle, they were describing a new kind of matter. Not matter in any exotic or hand-wavy sense, matter in the precise technical sense that physicists use when they talk about phases. You know about phases of matter in the ordinary sense: solid, liquid, gas. Ice, water, steam. 3 phases of the same molecule, each with its own structure and properties, separated by sharp transitions as you heat or cool them. You probably know there are others: plasma, when matter is hot enough that electrons are stripped free; superconductors, where electrical resistance vanishes below a critical temperature; superfluids, where certain quantum fluids flow without any friction at all. These are all equilibrium phases, all defined by what a system looks like when it has settled, when it has reached the long-run state that thermodynamics points it toward. A discrete time crystal is something different. It is a non-equilibrium phase. Its defining properties only exist in the driven, out-of-equilibrium setting. There is no way to see a time crystal by letting a system settle. The phase itself requires the constant nudging of the Floquet drive to exist, and it is the first rigorously described, experimentally testable example of such a phase of matter defined not by a pattern in space, not by some static arrangement, but by a pattern in time, by a persistent, robust, spontaneous rhythm. That's what the theorists had by the end of 2016, a mathematical framework, a clear mechanism, a prediction of a new phase of matter with a specific observable signature, a spectral peak at half the drive frequency, the unmistakable fingerprint of the period-doubled subharmonic response, stable against small perturbations, existing not in a fragile, one-off configuration, but as a genuine thermodynamic phase. And there was one more thing about that stability. One more property that the theory predicted and that deserves its own gentle moment in the telling, because it is perhaps the single most astonishing thing about the discrete time crystal. A physicist named Norman Yau, along with colleagues, made this explicit in a paper published in Physical Review Letters in 2017, Volume 118, Article 030401. And the property is this: the time crystal's period doubling is rigid. Think about what that means in practice. You're driving your system with a periodic pulse. The drive is supposed to flip the state of the system, let's say flip the spins of all the particles, perfectly every time. Ideally, you'd flip them by exactly 180 degrees, a perfect inversion. But in any real experiment, you can't be perfect. Maybe you achieve 174 degrees instead of 180. You're off by 6 degrees from the ideal. A small error, but an error. In a normal oscillating system, this kind of imperfection would accumulate. Each cycle, you're not quite flipping all the way, so the system drifts slightly. Over many cycles, the drift grows and the oscillation slowly degrades. It's like a clock that runs a little slow. Over time, it falls further and further behind. The imperfection matters. But in a discrete time crystal, something remarkable happens instead. Even if you flip the spins by only 174 degrees instead of 180, the system still reliably returns to exactly its starting configuration every 2 drive periods. It self-corrects, the error is absorbed. The rigidity of the phase means the period doubling is not sensitive to small imperfections in the drive. The subharmonic oscillation snaps back to exactly 2t, not 2t plus a small drift, not 2t minus a small drift, exactly 2t. This is not a coincidence. This rigidity is part of what defines a true time crystal, as distinct from a system that just happens to oscillate at twice the drive period by accident. A true time crystal emerging from a genuine phase transition should exhibit this robustness. It should be hard to move off its period. It should correct its own mistakes, the way a crystal's spatial order repairs itself around small impurities, the way the diamond's lattice persists even when a few atoms are missing. The order is a feature of the phase, not of the specific starting conditions. It belongs to the state of matter, not to the particular arrangement you began with. Flip it 174 degrees and it still answers at 2t. Flip it 176 degrees and it still answers at 2t. Flip it 171 degrees and still QDT 2t. The clock knows its own period better than the person trying to wind it. There's something in that which feels almost stubborn, almost willful, as if the system has decided what rhythm it belongs to and is simply refusing to be argued out of it. This is, of course, not willfulness, it is physics, but it is the kind of physics that earns the word elegant. So by the time 2016 gave way to 2017, the theory was in place. The discrete time crystal had been defined, its mechanism had been spelled out. The Foucault drive, the many-body localization, the subharmonic response, the rigidity. Its signature in the data had been predicted. That spectral peak at half the drive frequency, clean and sharp and stubborn. The landscape of theoretical physics had been carefully mapped. All that remained was to actually build one. And in 2017, in 2 different laboratories on the east coast of the United States, in 2 very different materials, using 2 very different experimental approaches, that happened almost simultaneously. The 2 results appeared back-to-back in the same issue of the journal Nature, published on March 9, 2017. If you read them side by side, they feel almost like a kind of stereo confirmation, 2 photographs taken from different angles of the same new terrain. The first came from the University of Maryland, from a group led by a physicist named Christopher Monroe. Monroe's team worked with something called trapped ions, atoms that have been stripped of 1 or more electrons, giving them an electric charge, which allows them to be held in place by electric fields, suspended in a vacuum, isolated from the world. If you want to know the specific atoms, ytterbium ions, the isotope with atomic mass 121, written 1 Yb+, 10 of them, a small chain of 10 charged ytterbium atoms hovering in a trap far from any surface, cooled to near stillness. These 10 ions each carry a quantum property called spin, a tiny magnetic orientation that can point, broadly speaking, in one of 2 directions. Think of it as each ion having a small internal compass needle that points either up or down. The state of the whole system is described by the combination of all 10 needles. And what Monroe's team did was apply the Foucault drive, periodic pulses of laser light that flip the spins, rotating them in a controlled way, and look for the signature of period doubling in the response. And they found it. The chain of ytterbium ions, driven at a particular frequency, responded at half that frequency. They saw the subharmonic peak. They varied the drive parameters and they deliberately introduced imperfections, and they saw the rigidity. The oscillation held its period even when the drive wasn't perfect. The result appeared in Nature, volume 543, pages 2 and 17. The paper's lead author is J. Zhang. The second result, appearing alongside it in the same journal, volume 543, pages 221, came from Harvard from a group led by Mikhail Lukin. And where Monroe's team had used 10 isolated ions, Lukin's team used a system that was larger by a factor of roughly 100,000. Their material was diamond. Ordinary diamond, almost. What made it interesting was not the carbon lattice itself, but impurities in that lattice. Defects where, instead of a carbon atom, there was a nitrogen atom sitting next to an empty site, a vacancy in the crystal. These nitrogen vacancy centers, often shortened to NV centers, are extraordinary things. Each one houses a quantum spin, similar to the spin in the ytterbium ions, but embedded in the solid material of the diamond rather than floating in a vacuum. And the diamond that Lukin's group worked with contained not 10 of them, but roughly 1 million. 1 million quantum spins woven into the structure of a piece of diamond, driven by microwave pulses. And from this very different physical setup, solid versus trapped, 1 million versus 10, microwaves versus lasers, the same signature emerged, the subharmonic response, the period doubling, the rigidity, the discrete time crystal in diamond. It's worth pausing on the fact that these two experiments, so different in their materials and methods, found the same phenomenon. That kind of convergence is deeply reassuring in experimental physics. A result found only in one very specific setup could, in principle, be an artifact, some quirk of the apparatus, some subtle experimental error, some feature of the particular material that happens to mimic the desired effect without actually being it. But when two different groups, using two different platforms with completely different physics in the details, arrive at the same signature, the same period doubling, the same rigidity, the same spectral peak at half the drive frequency, the confidence grows substantially. The theoretical framework predicted it. Two very different experiments saw it. The discrete time crystal, by the spring of 2017, had moved from an idea to an experimentally observed phenomenon. And yet, because in science there is almost always an "and yet," there were subtleties remaining, questions the community still had. The 2017 experiments were impressive, but the theoretical definition of a true, many-body, localized discrete time crystal has a particular precision to it. The time crystal order should not be a property of just one lucky initial configuration of the system. It should be a property of all the quantum states in the system, or more precisely, a property of the system's eigenstates, the fundamental quantum states that the system naturally settles into. This is what physicists call eigenstate order. It is the gold standard, the strictest version of the definition. Testing eigenstate order in a small chain of 10 ions or even in a million NV centers is difficult. The 2017 experiments saw the signature, yes. But how sure could you be that you were seeing a genuine, robust phase and not simply a long-lasting oscillation that would eventually decay, or an oscillation specific to the particular starting state rather than a true property of the phase? These were real questions, and they pointed toward a need for a more precisely controlled, more thoroughly tested demonstration. Which brings us to 2021 and to a processor called Sycamore, and to a collaboration that would be in many ways the most rigorous test the discrete time crystal had yet faced. But that is where this part of the story rests for now. The theory had done its work. The first laboratories had confirmed the signature. The physics community had a phenomenon to study, a phase of matter that existed not in equilibrium, but in the driven, non-equilibrium world, where the no-go theorems couldn't reach it. A phase that held its rhythm through disorder, that corrected its own imperfections, that refused to dissolve when the drive tried to heat it. There were still questions, there were naturally still questions. A result this strange and this new deserves scrutiny, deserves the most careful and demanding tests that experimentalists can devise. And those tests were coming. They were being planned in 2017 and 2018 and 2019 in laboratories and on quantum processors that were, in those years, still being built, still being calibrated, still learning to do the things that the theorists needed them to do. The time crystal had been born, but the story of what it really is, whether it is truly the phase the theorists described, rigid and eigenstate-ordered and genuinely non-equilibrium, that story was still being written. And somewhere in Mountain View, California, a team of physicists and engineers was working with a machine that might, finally, be precise enough to answer those remaining questions with the clarity the physics demanded. That's where we're going next. But for now, if you need to let this part settle, the impossible declared, the rescue found, the first crystals glimpsed in ytterbium and diamond, that's a good place to rest. There's no rush. The Sycamore processor will still be there when you come back. So let's sit with what that means for a moment. The time crystal is ticking. In the Maryland lab, those 10 ions of ytterbium-171 are flipping back and forth in their period-doubled rhythm. In the Harvard diamond, 1 million nitrogen vacancy centers are oscillating at half the drive frequency, steady and locked. The experiments had worked. The signatures were there in the data, real and reproducible. But a question had been building all this while, and you might have felt it gathering at the back of your mind even as we walked through the physics together. It's the most reasonable question in the world, and it deserves a full and honest answer before we go any further. If something is moving perpetually and without stopping, doesn't it need energy to do that? And if it doesn't need energy, then if it really, truly ticks without burning anything, then isn't that precisely the thing physicists have spent 3 centuries insisting is impossible? Perpetual motion, free energy. The one class of machine that the laws of thermodynamics forbid so absolutely that the patent offices of several countries have official policies rejecting applications for it without examination. It's a fair question. It's in fact the right question. And the answer, and the real answer, not the simplified one, is one of the most beautiful pieces of physics reasoning I know. Let's take it slowly. When you hear perpetual motion machine, what the physics is actually forbidding is something specific. It's a machine that does useful work indefinitely without any energy input, a wheel that spins forever and powers a generator, an engine that runs without fuel and lifts weights. Something that takes the ambient heat of a room and converts it into ordered mechanical work, violating the second law of thermodynamics in the most direct and catastrophic way. The second law says that in a closed, isolated system, one with no energy flowing in and no energy flowing out, entropy, disorder, always tends to increase or stay the same. You cannot spontaneously create order from chaos. You cannot run a heat engine with only one reservoir at a single temperature. You cannot, in short, get something from nothing. Now here is the key thing about a time crystal. It is not a closed, isolated system. Pause and let that land. Remember the Floquet drive we talked about, the periodic kick that the experimentalists apply to the system every T seconds like a metronome tapping its foot. That drive is an energy input. The time crystal is not sitting quietly in a sealed box, untouched by the outside world, generating its own motion from nothing. It is connected by that drive to an external energy source. Energy is flowing in. So the second law, in its strictest form, simply doesn't apply to this system in the way the perpetual motion framing implies. The law applies to isolated systems. A time crystal isn't isolated. The drive is there, ticking away, pouring energy in. The second law is not being violated. It is not even being brushed up against. But then you might reasonably say, well, if energy is flowing in, then what's special about this? Plenty of things oscillate when you drive them. A child on a swing oscillates when you push it. A radio antenna oscillates when you feed it an electric current. Why is a time crystal different? And this is where the story gets genuinely surprising, because yes, the drive is there, but the time crystal is not doing what a driven system ordinarily does with the energy it receives. Normally, when you drive a system periodically, when you poke it over and over with a regular oscillating force, two things can happen. Either the system resonates and absorbs the energy efficiently, heating up, vibrating more and more violently until something breaks. Or if it's a simple harmonic oscillator like a clock pendulum or a quartz crystal, it loses energy to friction or resistance at the same rate it gains it, settling into a steady oscillation where the input and the loss balance. In neither of these cases is the system doing nothing with the energy. In the first case, it's heating up. Energy is accumulating as thermal disorder, which is what generic, periodically driven quantum systems do if you don't design them carefully. Physicists call this heating to infinite temperature, meaning the system absorbs energy from the drive until its quantum states are completely randomized, like a deck of cards that's been shuffled so thoroughly that every possible ordering is equally likely. That is thermal death for the crystal. No time, crystal survives it. And in the second case, the clock pendulum case, energy is being continuously lost to air resistance, to friction in the bearings, to electrical resistance in the circuit, and continuously replaced by the drive. Remove the drive and the oscillation decays. The drive is doing work in the technical sense. It's fighting entropy, replacing what's lost, maintaining the motion against dissipation. A time crystal, in the ideal theoretical picture, does neither of these things. It doesn't heat up, and it doesn't dissipate energy that needs to be replaced. How? This is where we have to meet a concept called many-body localization. And I want to spend a little time with it because it's the secret mechanism, the hidden trick, the thing that makes the whole remarkable phenomenon possible. Most accounts of time crystals mention it in passing. Let's actually look at it. Imagine you have a system of many quantum particles, either electrons or ions or qubits, that are interacting with each other and with a disordered landscape. By disordered, I mean that each particle sits in a slightly different environment. The potential energy around it, the local magnetic field it feels, the particular frequency at which it wants to vibrate, all of these vary from particle to particle, seemingly at random. It's like a city where every house has a slightly different room temperature, a slightly different elevation, a slightly different set of plumbing quirks. Now, ordinarily, if you heat one corner of this city, but if you give energy to a few particles, that energy will spread, it will diffuse, it will conduct its way from the hot corner to the cold corners, the way heat always flows in a normal material until everything reaches the same temperature. This is called thermalization. It is, in a deep sense, what the second law of thermodynamics is about. Systems spread their energy until disorder is maximized. But in a many-body localized system, this spreading doesn't happen. The disorder is so strong, and the way interactions scatter quantum phases creates such a kind of quantum interference that energy becomes trapped, localized, stuck. A particle that receives extra energy keeps it. The disturbance can't propagate. The heat can't flow. It's a bit like imagining that in that city, every path between houses has been completely blocked by enormous fallen trees, and the trees are so numerous and so randomly placed that there is no route, no matter how circuitous, that connects one house to another. Energy has nowhere to go, it stays put. In a many-body localized system, the quantum version of this happens. The disorder, the random variation in particle environments, combined with the interactions between particles, creates a quantum traffic jam so thorough that the system simply refuses to thermalize. It never heats up. It never scrambles its quantum information. It sits, in some sense, frozen in its initial configuration forever. And this very specific, very unusual property is what saves the time crystal from the fate that kills every generic-driven system. When the Floquet drive pokes a many-body localized time crystal, the energy from the drive cannot spread through the system. The localization stops it. The crystal absorbs the poke, flips its pattern in the period-doubled rhythm we've been discussing, and then that's it. The energy doesn't dissipate as heat. The system doesn't scramble. It doesn't gradually randomize. It holds its pattern exactly and rigidly and waits for the next poke. And so from the outside, from the perspective of an observer watching the crystal over time, it looks like something is oscillating forever without consuming energy. And in a meaningful sense, it is. The energy the drive puts in is not being converted into useful work. And it's not being converted into heat. It's going nowhere. The system is locked. The localization is so total that the energy has no pathway to flow into. This is why the time crystal doesn't violate the second law. The drive is there, yes, but the crystal isn't actually absorbing net energy from the drive in the way a normal oscillator would. The drive pokes it, it flips, and the energy stays frozen. Nothing accumulates, nothing dissipates. The crystal oscillates, but it does no work. Now, before we go further, I want to be very direct about something that comes up whenever this topic is discussed in public. You will sometimes see headlines saying that time crystals could power devices forever, that they could serve as batteries that never run out or engines that require no fuel, that they represent a path to free energy. This is not true. And understanding exactly why it's not true is actually the most satisfying part of the whole story, because the reason reveals something fundamental about how nature is constructed. To extract usable energy from a system, to use it to do work, to power a motor, to charge a battery, to light a bulb, you need to couple that system to something external and allow energy to flow. You need a connection, a pathway, through which the ordered motion of the system can transfer into the mechanical or electrical work you want it to do. But the moment you create that pathway, the moment you attach a wire, a load, a mechanism that can draw energy out, you have done something catastrophic to the time crystal. You have connected it to an external environment. You have given the localization a channel through which to break down. The disorder that was keeping everything frozen, the quantum traffic jam that was preventing thermalization, it starts to leak. The very property that makes the time crystal tick forever is the property that makes it impossible to tap. If you try to draw energy from a time crystal, you destroy it. The oscillation decays. The phase breaks down. The crystal melts back into an ordinary driven system and heats up, exactly as a generic Floquet system would. You get a brief burst of something and then thermal death. There is no free lunch. Nature knew this already. The conservation laws did not miss a loophole here. The time crystal's eternal motion is real, but it is motion that is, in a precise technical sense, perfectly useless, beautiful, fundamental, but useless for powering anything. And I want to sit with that for a moment because there's something almost poetic about it. Nature allows a thing to move forever, and the price it charges for that permission is that the motion cannot be used for anything else. The crystal ticks, and the tick goes nowhere. It is motion for its own sake, a rhythm that echoes through time and does not disturb a single joule of anything outside itself. There is a similar thing to say about the battery-free clock framing that sometimes appears in popular accounts. Remove the Floquet drive, switch it off, stop the periodic kicks, and the time crystal stops. Just like that. There is no stored energy keeping it going. The drive was the engine. The localization was what prevented the engine from overheating, but without the engine, there is no motion. A clock built from a time crystal still needs something to power the drive, which means it still needs a battery or a power source. It's not a battery-free device. It's a device with an unusually stable response to the power source it has, which is still remarkable, but it's a different kind of remarkable than the headlines suggest. And one more thing while we're clearing the air. Occasionally, in the corners of the internet where physics gets tangled with speculation, you'll find time crystals mentioned alongside time travel, as if a crystal that repeats in time might be a first step toward moving through time, or reversing it, or accessing the past. This is a misunderstanding of what time means in the name time crystal. When we say the crystal repeats in time, we don't mean it moves through time, or that time flows differently inside it, or that it has any unusual relationship to the arrow of time at all. We mean simply that its physical configuration repeats as time passes. Its pattern at moment t is the same as its pattern at moment t plus 2t. That's it. It's a description of a pattern in time, exactly as a spatial crystal's pattern repeats across space. The word time here is about periodicity, not about time travel. A time crystal no more travels through time than a striped shirt travels through space. The stripes repeat. That's what periodic means. Now, with all of that settled, the second law intact, the perpetual motion debunked, the confusion cleared, we can come back to the physics itself and meet something genuinely strange. Because even without the misconceptions, even shorn of everything that was never true, the time crystal remains one of the more remarkable things in recent experimental physics. And one of the most remarkable things about it is a property called rigidity. Rigidity is, in a sense, what separates a true time crystal from a trivially oscillating system. It's the signature that tells you the system has really broken time translation symmetry, that it really is a new phase of matter and not just a collection of spins that someone tickled into a pattern that will eventually dissolve. Here is how it works. In a real experiment, nothing is perfect. When you try to flip all the spins in a system by exactly 180 degrees, turning every upspin into a downspin, you will not quite succeed. You might flip by 174 degrees or 183. Your laser pulse will have some imperfection, some timing jitter, some miscalibration. And if you're just driving a collection of spins that happen to be oscillating in a period doubled pattern due to some accidental resonance, those imperfections matter enormously. A 174-degree flip instead of a 180-degree flip will produce a response at a slightly different period. The oscillation will drift, it will dephase. Over many drive cycles, the imperfection will accumulate and the periodic pattern will smear out and disappear. But in a true time crystal, this doesn't happen. You flip by 174 degrees and the crystal still responds at exactly 2t. It corrects itself. The period snaps back to exactly half the drive frequency, as if the imperfection had never occurred. The crystal has, in some sense, absorbed the error and refused to propagate it. This is the rigidity, and it comes, again, from the combination of the many-body localization and the broken symmetry. The time crystal's period isn't an accident of fine-tuned driving, it's a consequence of a phase of matter. Just as you cannot continuously deform a crystal lattice by nudging individual atoms, the lattice either is crystalline or it isn't, and a small perturbation doesn't change its fundamental period. A time crystal's temporal period is similarly rigid. Small imperfections in the drive don't break the symmetry, they don't shift the period, they're absorbed, corrected, dismissed. Norman Yao and his collaborators, in a paper published in Physical Review Letters, Volume 118, Article 030401 in 2017, spelled out the diagnostics for a true discrete time crystal in careful theoretical terms. The rigidity, the persistence of the period doubled response even under imperfect driving, was one of the key criteria. If you perturb the drive and the period shifts proportionally, you don't have a time crystal, you have an oscillating system. If you perturb the drive and the period holds steady, locked at 2t regardless of the size of the perturbation, you have something genuinely new, the self-correcting clock, a rhythm that insists on itself. And this is part of why the 2017 experimental results were so significant and worth spending a moment with before we move on to the later, more precise experiments. On March 9, 2017, two papers appeared back-to-back in Nature, published simultaneously and deliberately paired, two different experimental groups reporting the observation of discrete time crystal signatures in two entirely different physical systems. The first was from the laboratory of Christopher Monroe at the University of Maryland. Monroe's group had been working with trapped ions for years, individual atoms caught in electromagnetic traps and held almost perfectly isolated from their environment. For this experiment, they used a small chain of 10 ions of ytterbium-171, an isotope of ytterbium, each of which carries a nuclear spin that can be controlled with laser pulses. 10 ions, a tiny, tiny system, a chain you could line up end to end and still not span a single human hair. And yet in those 10 ions, Monroe's team saw it. They applied a Floquet drive, a sequence of operations repeated periodically, a spin flip pulse, an interaction step that introduced the kind of disorder needed for many-body localization, a measurement. They varied the spin flip angle, deliberately introducing exactly the kind of imperfection that would wash out any trivial oscillation. They watched the response of the ions, and there, in the data, was the subharmonic, the response at half the drive frequency. When they drove the system with a period t, the ions collectively flipped and returned to their starting state every 2t. Not sometimes, not approximately. Every time, exactly, locked, rigid, even when the flip angle was imperfect. The paper, Zhang et al., Nature, volume 543, page 217, reported this observation with appropriate caution, noting the finite size of the system and the challenges of ruling out every alternative explanation. But the signature was unmistakably there. The second paper came from the laboratory of Mikhail Lukin at Harvard. Lukin's group had taken a completely different approach, using a system that could not be more different physically from Monroe's tidy chain of 10 ions. Their system was a diamond. Specifically, a small piece of diamond that had been deliberately doped, implanted with defects, impurities, tiny locations where the otherwise perfect carbon lattice had been disrupted by a nitrogen atom sitting next to an empty space in the crystal. These defects are called nitrogen vacancy centers, and each one contains a single electron spin. Lukin's group had packed approximately 1 million of these nitrogen vacancy centers into their diamond sample. 1 million spins, each one a tiny quantum magnet embedded in the imperfect diamond lattice. The disorder in a real diamond, the random distribution of those impurities, the slight variations in local magnetic fields, the thermal noise, provides, in this system, a natural source of the kind of disorder that many-body localization needs. The system is already imperfect, already disordered, and the interactions between those million spins, mediated by the diamond lattice, create the many-body dynamics. Lukin's team drove the diamond with microwave pulses, periodically flipping the nitrogen vacancy spins. They watched for the subharmonic response. They varied the flip angle to test for rigidity. The result, Choi et al., Nature, volume 543, page 221, reported time crystal signatures in the diamond. The period-doubled response, the rigidity, the persistence of the subharmonic even under imperfect driving in a system of 1 million spins at room temperature. Two completely different systems. Trapped ions, laser-cooled to near absolute zero in an ultra-high vacuum. A room temperature diamond, noisy and imperfect, bristling with 1 million electron spins, and both of them showing the same signature. That convergence mattered enormously. When two entirely different physical platforms built by different groups using different techniques produce the same qualitative behavior, it is very difficult to attribute the result to a quirk or an artifact specific to one system. The phenomenon, whatever it is, appears to be robust. But the physics community was careful. These were beautiful results. They were genuinely surprising and significant results, but they raised as many questions as they answered. The Maryland system had only 10 ions. 10 is not very many. In principle, a true time crystal, in the theoretical definition that Elsa and Kemani and Nyack and the others had developed, should be a property of a system in the thermodynamic limit, meaning a very large system, ideally infinite in size. 10 ions is far from infinite. It's possible, some theorists argued, that the observed rigidity was partly a finite size effect, a consequence of the small system size that would eventually dissolve if the chain were made longer. The Harvard diamond had 1 million spins, which is a much larger system, but the diamond has its own complications. It is a three-dimensional system with complex interactions, and the disorder is natural rather than precisely controlled, which makes it hard to verify that the system is truly in the many-body localized phase, as opposed to some other phase that might mimic the signatures. And in both experiments, as with any quantum system, there was the question of decoherence. Quantum systems are fragile. They interact with their environment, with stray magnetic fields, with vibrations in the apparatus, with thermal fluctuations. And these interactions cause the quantum coherence that makes the time crystal possible to gradually decay. How do you know that what you're seeing is a genuine time crystal signature and not just the slow decay of an initially coherent state that happens to look periodic for a while? These were not idle, skeptical questions. They were the right, scientific questions, the ones that any careful physicist would need to ask before concluding that a genuinely new phase of matter had been observed. And answering them required something more, a platform with precise individual control over each constituent, so you could program in exactly the disorder you needed, not just accept whatever disorder nature happened to provide. A platform large enough to approach the thermodynamic limit more closely than 10 ions could manage, and a platform with the ability to run careful cross-checks. Experiments designed not just to show the phenomenon, but to actively rule out the alternatives. Those questions were about to get answers. Not from a diamond, and not from a chain of trapped ions, but from a quantum processor built by a team in Mountain View, California, using a chip called Sycamore. But there is something I want to pause on before we get there, because it's easy to move through the 2017 results quickly and miss what was actually remarkable about them. Christopher Monroe's 10 ytterbium ions strung in a chain inside a vacuum chamber, each one held in place by electric fields, each one talked to by lasers calibrated to frequencies so precise they took years to perfect. That is an extraordinary achievement of experimental physics. Each ion is a single atom, a single atom. The nucleus contains 70 protons and 101 neutrons. Around it orbits an electron whose spin is the qubit, the piece of quantum information being manipulated. And Monroe's team could address each of those 10 atoms individually, could flip its spin, could read its state, could watch it interact with its neighbors with a precision that would have seemed like pure fantasy to physicists of a generation earlier. And Mikhail Lukin's diamond. Think about what a nitrogen vacancy center actually is physically. It is an atom of nitrogen, one atom, a single nitrogen, sitting in a diamond lattice where a carbon atom should be, right next to a gap, a vacancy, an absence. And in that absence, an electron is trapped. Its spin is a quantum system, a two-state quantum system that can be initialized and read and controlled optically. One atom and one missing atom, and between them a qubit. And Lukin's sample had 1 million of those. Not identical, not perfectly arranged, but all there, all contributing to the collective quantum behavior that produced the period-doubled oscillation in the data. There is something humbling about the scale of experimental precision these results required. The time crystal was a theoretical idea for only 5 years before real experiments produced real data. In the history of quantum physics, that is a remarkably short journey from proposal to observation. The tools existed, the techniques existed, the theoretical predictions were specific enough to be testable, and the experimentalists had the skill to test them. The signature of the time crystal in the data is, in a technical sense, quite clean. When you plot the frequency spectrum of the spin oscillations, when you take the response of the spins over time and perform a mathematical transform to see which frequencies are present, you see a peak, a sharp, distinct peak. Not at the drive frequency, not at the frequency the experimentalists are applying their pulses, but at exactly half that frequency. If the drive has period t, the response has period 2t, which means its frequency is half the drive frequency. That peak, sitting at precisely half the drive frequency, sharp and stable, and robust against variations in the drive parameters, is the smoking gun. It is the subharmonic response that the theory predicted. It is the signal that the system is not merely oscillating at the pace of its poke, but has settled into a pattern that is genuinely distinct from the driver. A pattern that is self-organizing, a pattern that, in the language of the theory, represents a broken time translation symmetry. The two Nature papers from March 9, 2017, were the first times that peak had been observed in any experimental system in the world. 5 years after Wilczek's proposal and 2 years after the no-go theorems appeared to close the door on the whole idea, the door had been opened again. Not just in theory, but in the data of real experiments. The time crystal was real, its motion was real, its rigidity was real, and the physics community was paying attention. It was paying attention and asking more questions, because the deepest, most rigorous theoretical definition of a discrete time crystal is not just a system that shows a period-doubled response. It is a system whose time crystal order is a property not of one particular initial state you chose to start with, but of all its eigenstates. A system where no matter which state you start from, no matter which quantum configuration you initialize, you see the same period-doubled pattern in the long-time behavior. This property, eigenstate order, is the thing that truly distinguishes a time crystal as a phase of matter, as something universal and not contingent on a lucky initial condition. And testing for eigenstate order properly requires something that the 2017 experiments could not easily provide: the ability to prepare many different initial states and compare their behavior systematically. That test would require more programmable control than a diamond and more qubits than 10 ions. It would require, in a word, a quantum processor. A machine designed from the ground up to initialize arbitrary quantum states, apply precise sequences of operations to them, and read out the results. And in 2021, that machine was ready. The Sycamore processor, built by Google Quantum AI, is a chip containing superconducting qubits arranged in a two-dimensional grid. Each qubit is a tiny superconducting circuit, a loop of metal cooled to just a fraction of a degree above absolute zero, a temperature so cold that the quantum behavior of the electrons dominates entirely, and the circuit can be made to behave like a two-state quantum system. A qubit and the qubits on Sycamore can be individually addressed and controlled, each one independently programmable, each one capable of being initialized into a specific state and coupled to its neighbors with precisely tunable interaction strengths. The team that used Sycamore to study time crystals included researchers from Google Quantum AI itself and collaborators from a number of institutions: Stanford, Princeton, Oxford, and the Max Planck Institute, among others. Vedika Kamani, one of the Princeton theorists who had co-authored the foundational theoretical papers on discrete time crystals in 2016, was directly involved in the experimental collaboration, which meant that the people running the chip included some of the same people who had written the theory the chip was meant to test. The experiment used 20 of Sycamore's qubits, 20 superconducting quantum objects, each one a tiny loop of metal cooled to temperatures colder than outer space, each one individually controllable, each one an element in what would become, for a few hundred drive cycles, a time crystal. And the results, published in Nature, volume 601, pages 531 through 536, appearing online in November of 2021 and in print in 2022 under the title Observation of Time Crystalline Eigenstate Order on a Quantum Processor, were, in several important ways, a step beyond what the 2017 experiments had achieved. We'll get into precisely what made those results stronger. The eigenstate order test, the program disorder, the time reversal echo protocols that let the team distinguish genuine time crystalline behavior from the slow, quiet death of decoherence. When we continue, because that distinction between real-time crystal order and something that merely looks like it is one of the subtler and more important stories in recent experimental physics, and it deserves the space and the quiet to unfold properly. For now, though, hold on to what we have. The second law of thermodynamics is intact. No free energy, no battery-free clocks, no perpetual motion machines in any useful sense. The drive is there, and without it, the oscillation stops. The time crystal is an open, driven, non-equilibrium system, and that is precisely why it can exist. It found its loophole not by breaking the rules, but by operating in a regime where the rules that seem to forbid it simply don't apply in the way you might expect. And within that regime, it does something genuinely strange. It ticks without heating up. It oscillates without dissipating. It holds its period rigidly in the face of imperfection, self-correcting, settling back to its locked rhythm every 2 drive cycles, as if time itself had its own preferred beat. 2 labs found that beat in 2017, and in ytterbium ions, and in diamond, and the world of physics tilted slightly on its axis. What comes next is the more rigorous reckoning, the deeper test, the machine that could tell you not just whether the system oscillated, but whether that oscillation was truly, universally, fundamentally a property of the phase. Not a lucky one-off, not a decoherence artifact, not a trivial echo, but the real thing. Rest here for a moment if you need to. The science can hold. The ions are still ticking in their chain. The diamond is still humming with its million-spin chorus. And somewhere in Mountain View, a chip called Sycamore is cooling toward its working temperature, 40 millikelvin above absolute zero, waiting for its instructions. And so we come to the machine. Not a machine in the way your kitchen kettle is a machine, or the way the gears of a clock are a machine. Not something you could hold in your hand or watch spinning. Sycamore is a quantum processor, a device small enough to sit on a table, but kept at a temperature colder than deep outer space, colder than the cosmic microwave background radiation that drifts between galaxies, cooled to within 40 millikelvin of absolute zero in a refrigerator the size of a chandelier. At that temperature, matter behaves in ways that have no ordinary world analogy. Quantum effects dominate everything. The ordinary rules of hot and cold, of information as something solid and classical, dissolve into a regime where superposition and entanglement are the natural language. This is where the time crystal came home. In November of 2021, a collaboration involving Google Quantum AI, Stanford, Princeton, Oxford, the Max Planck Institute and others published a paper in the journal Nature, volume 601, pages 531 to 536, with a title so precise it sounds almost bureaucratic. Observation of Time Crystalline Eigenstate Order on a Quantum Processor. The lead author was Xiao Mi from Google Quantum AI. Among the collaborators was Vedika Khemani, one of the theoretical physicists from the 2016 group whose work had rescued the concept of the discrete time crystal in the first place, who had helped prove that such a thing could exist, and who now found herself helping to prove that it actually did. 20 superconducting qubits. That's the number you want to hold in your mind as we go through this. Not a million nitrogen vacancy centers, not even 10 trapped ions. 20 individual qubits, each one a tiny superconducting circuit, each one capable of existing in a superposition of its two states until you measure it. 20 is not a large number by ordinary standards, but in this context it was enough. It was enough to create something that had never quite existed so cleanly before. Let's take a moment to understand why this experiment was different, why it wasn't just another instance of the same thing Christopher Monroe had done in Maryland or Mikhail Lukin had done in Harvard. Because the 2017 experiments were extraordinary, genuinely. They saw the signature, the period-doubled response, the subharmonic oscillation that shouldn't have been there according to the simplest reading of the drive. But there were questions. There are always questions in physics. The system you build in a lab is never exactly the system you described in your theoretical model, and the gap between them is where doubt lives. Here is one of those doubts. Imagine you set up a system and you drive it with a periodic pulse, and you observe that the system responds at half the drive frequency. It oscillates with period 2t when the drive has period t. That is the signature you're looking for. But what if the oscillation you're seeing isn't actually the time crystal order? What if it's just the system ringing, like a bell that has been struck and is now vibrating at its own natural frequency, which happens to be close to half the drive frequency by coincidence? That kind of trivial subharmonic is not a phase of matter, it's just a resonance. It would be embarrassing to confuse the two. And here is a deeper doubt. What if the oscillation you're seeing is partly, or largely, an artifact of decoherence itself? Decoherence is the enemy of quantum systems. It's what happens when the quantum system starts leaking information into its environment, losing its quantum character, behaving more and more classically. In principle, a decohering system could produce oscillations that look superficially like time crystal behavior, but have nothing to do with genuine many-body, localized, discrete time crystal order. You could be measuring the process of your quantum system falling apart and calling it a crystal. Both of these doubts apply in some degree to any real experiment. No experimental system is perfectly isolated. No drive is perfectly tuned. The question is how carefully you can rule out the imposters. This is where the Sycamore processor gave the collaboration something they hadn't had before. The first advantage was programmability. Each of the 20 qubits in the Sycamore time crystal experiment could be individually controlled. You could program, qubit by qubit, exactly how strongly each one interacted with its neighbors and exactly what kind of disorder. The ingredient so crucial for many-body localization, the randomness that freezes the system and prevents it from heating up, was imposed on each site. In the trapped ion and NV center experiments, disorder existed, but it wasn't fully programmable. You took what the material gave you. Here, you could dial in disorder precisely, tune it, verify that it was doing what the theory demanded. The many-body localization wasn't something you hoped was present. It was something you built in deliberately, qubit by qubit. Think of what that means. Many-body localization, as we've talked about in earlier parts of this journey, is the phenomenon that saves the time crystal from its own thermodynamic doom. It's what prevents the driven system from absorbing more and more energy from the periodic drive, heating up endlessly, eventually reaching a featureless, infinite temperature state where all memory of structure, all memory of oscillation, all memory of the initial configuration is erased. Without many-body localization, a driven quantum system dies that way. It heats to death. With it, the system's energy becomes frozen in place, unable to flow, unable to distribute itself thermally. The crystal can oscillate without warming up because the warmth has nowhere to go. In the Sycamore experiment, you could turn this knob, you could tune the disorder and watch the time crystal behavior emerge or fade depending on whether the many-body localization was sufficiently strong. That's not just an observation. It's a controlled demonstration of the underlying mechanism. It's the difference between finding a plant growing through a crack in the pavement and actually understanding why roots split rock. The second advantage was range. In the 2017 experiments, the researchers typically prepared one carefully chosen initial state, drove it, and watched it oscillate. This tells you something, but the theoretical definition of an eigenstate ordered phase, the idea that the time crystal behavior is not just a property of some lucky initial condition, but a property of the phase itself, of all the energy eigenstates of the system, demands more than one initial state. It demands that you see the same behavior regardless of where you start. If you prepare 10 different initial configurations of your 20 qubits, 10 different patterns of spin up and spin down, chosen to be as varied as possible, and you run the drive on each one, and you see the same period-doubled oscillation in all of them, that is much stronger evidence. It tells you the oscillation isn't an accident of the starting point. It's built into the structure of the quantum phase. The Sycamore team did exactly this. They swept across many different initial states and confirmed that the subharmonic response was there regardless of how they started. That's the eigenstate order in the title of the paper. Not just order in one state, order throughout the spectrum. But perhaps the most elegant piece of the experiment was what they did about decoherence, about the fear that what they were seeing was not a time crystal at all, but simply a quantum system dying in a particular way. The protocol they used was a kind of time reversal, sometimes called an echo sequence, and it is worth slowing down to appreciate it because it is beautiful. Here is the idea. Quantum mechanics at the microscopic level is time reversible in a way that everyday classical physics is not. If you run a quantum circuit forward, evolving qubits through a sequence of operations, and then run it backward, inverting every operation in reverse order, you should, in principle, return to exactly the state you started in. The laws of quantum mechanics don't have a preferred direction of time, at least not at this level. This is unlike heating a cup of tea. Pour hot water in, wait, and the tea cools. You can't reverse that process just by waiting some more. But for a small quantum system running through a sequence of unitary operations, you can. Now, if decoherence is significant, if the system is leaking information into its environment, if it's behaving in ways that are not fully reversible, then when you run the circuit backward, you will not recover your initial state. The information that leaked out is gone. The time-reversed run will look different from what a fully coherent system would produce, and that discrepancy tells you exactly how much of what you're measuring is genuine coherent quantum behavior and how much is decoherence noise. The Sycamore team ran their time crystal drive, measured the subharmonic oscillation, and then applied this echo protocol. They ran the circuit forward for some number of cycles, then reversed it and compared. What they found was that they could quantitatively separate the signal of genuine time crystalline behavior from the noise of decoherence. The period-doubled oscillation persisted in ways that decoherence alone couldn't explain. The echo protocol gave them a kind of decoherence subtraction, a way of looking through the noise to the real signal underneath. This is the smoking gun, not just a peak at half the drive frequency in the spectrum, though that is there too, sitting cleanly and distinctly above the noise, exactly where the theory predicts it should be. But a peak that survives the time reversal test. A peak that is robust across many initial states. A peak that appears and strengthens as the programmable disorder is tuned into the many-body localized regime and fades as the disorder is reduced. 3 independent lines of evidence converging on the same answer. The time crystal is real, and it was sitting inside 20 superconducting qubits running on a chip designed for quantum computation, cooled to 40 millikelvin in a dilution refrigerator in Mountain View, California, for a run that lasted on the order of hundreds of drive cycles before the inevitable limits of the real world, finite size, residual environmental coupling, imperfect localization, began to soften the signal. We should be honest about that number, hundreds of drive cycles, not a billion, not a trillion. Not quite forever in any everyday sense of the word. And yet, this is important, the theoretical prediction is that in the idealized case, a perfect many-body localized discrete time crystal would maintain its period-doubled oscillation indefinitely. As time approaches infinity, the oscillation does not decay. The hundreds of cycles in the lab are not the theory. They are a real system approaching the theory, a finite approximation of an infinite ideal, squeezed by the realities of quantum hardware that even Google can only approximate. You are not a perfect sphere, and you don't roll quite frictionlessly down an inclined plane, but the theory of a perfect sphere on a frictionless plane tells you something profoundly true about how you move. The same is true here. The hundreds of cycles are not the point. The point is what they are pointing at. Something can, in principle, tick forever. Without dissipating, without warming up, without doing any work, without violating a single law of thermodynamics. That is what the Sycamore experiment confirmed in the most careful, most controlled, most theoretically rigorous way yet achieved. Let the implications of that settle if you can before you fall asleep. Now. The world didn't stop there. It rarely does. In the same year, 2021, and spilling into 2022, a different kind of time crystal began to appear in laboratories. Not the discrete time crystal, the one that breaks the discrete periodic symmetry of an explicit drive. A new kind, the continuous time crystal. Here is the distinction, briefly and gently. The discrete time crystal we've been talking about all night is driven. There is an external periodic poke, a Floquet drive with period t, and the system responds at 2t. The symmetry that is broken is the discrete time translation symmetry of the drive. Every t seconds, the drive looks the same. But the system chooses to look the same only every 2t seconds, breaking that periodicity. A continuous time crystal is different in a subtle and interesting way. It doesn't need a periodic drive at all. It spontaneously develops an oscillation from a non-equilibrium but not periodically driven condition, breaking continuous time translation symmetry, which is closer in spirit to what Wilczek originally proposed in 2012. Remember Wilczek's original question, can a system in its ground state spontaneously oscillate? The no-go theorems of Bruno and of Watanabe and Oshikawa proved you can't do this in thermal equilibrium. But outside equilibrium, in a system that is being maintained in a non-equilibrium steady state, fed by some source of energy but not driven with a periodic kick, the question is different. And the answer, it turned out, is yes. A group working with a Bose-Einstein condensate, a cloud of ultra-cold atoms cooled to such low temperatures that they all collapse into the same quantum state, behaving as a single coherent quantum object, placed inside an optical cavity. A kind of trap made of laser light bouncing between mirrors was the setting. The group associated with this work included researchers in Hamburg. Hendrik Kessler and colleagues published results in Physical Review Letters in 2021, and work from related approaches appeared in Nature in 2022, demonstrating that such a system could develop spontaneous, sustained oscillations. A rhythm that arose not because something was hitting it periodically from outside, but because of the quantum dynamics of the system itself, maintained by the continuous pump of light feeding the cavity. The Bose-Einstein condensate begins to oscillate, not because it was told to, in a sense, because in the non-equilibrium steady state it inhabits, oscillation is the energetically preferred configuration. The system breaks continuous time translation symmetry of its own accord. This is remarkable for a different reason than the discrete time crystal. It is closer to what Wilczek dreamed about in 2012, a system that develops its own internal clock, not borrowed from an external metronome. The oscillation is the system's own. The cavity and the pump feed it, maintain the non-equilibrium conditions it needs, but the period of the oscillation is chosen by the system, not imposed from outside. And one of the things that makes this class of results particularly striking is where it has started to appear. By 2022, continuous time crystals had been observed not just in exotic, near absolute zero laboratories, but at room temperature. Systems at the temperatures of an ordinary room, without any elaborate refrigeration, were showing time crystalline behavior, which suggests that this phenomenon is not some fragile exotic artifact that exists only in the most extreme corners of experimental physics. It is something more robust, something that nature, given the right conditions, reaches for quite readily. What we are describing, alter both the discrete time crystal and the continuous time crystal, is something that doesn't fit neatly into the old categories. You learned at some point in your life that matter comes in phases: solid, liquid, gas. You may have also learned about plasma, that fourth phase where the gas is ionized, stripped of electrons, conducting electricity, shimmering at the temperatures of stars. You may even have heard of superconductors, where electrons flow without resistance, or superfluids, where liquid helium at very low temperatures flows without viscosity. All of these are phases of matter. They are defined by their symmetries, their response functions, the ways they organize themselves at low energy. Every one of those classical phases, and the more exotic quantum phases, is defined in thermal equilibrium. The superconductor is an equilibrium phase. The superfluid is an equilibrium phase. Even the plasma, in principle, can be treated as a system in local thermal equilibrium. The rules of thermodynamics, the partition function, the free energy, all the tools of statistical mechanics that let physicists classify and understand phases of matter, assume equilibrium, or something close to it. Time crystals are something else. They are the first established example of a non-equilibrium phase of matter, a phase that exists only in systems that are away from equilibrium, either driven periodically or maintained in a non-equilibrium steady state, a phase that cannot be understood with the classical tools of equilibrium statistical mechanics at all. To describe a time crystal, you need a new language: Floquet theory, eigenstate thermalization, and its absence, many-body localization, the mathematics of driven quantum systems that physicists have spent the last decade developing precisely because they needed it for things like this. This is what physicists mean when they say a time crystal opens a new classification of matter, not just a new example within an old category, a new category, a door into a wing of the palace that wasn't on the map. And it's a wing that, once opened, turns out to be large. The non-equilibrium world is full of phenomena that equilibrium physics can't capture. Your own body is a non-equilibrium system. You maintain your structure and your temperature and your heartbeat by continuously consuming energy and expelling it as heat. Living things are emphatically not in thermal equilibrium, and the fact that biology produces such sustained, organized periodic behavior, your heart beats with extraordinary regularity, without violating thermodynamics, is exactly the kind of thing that a mature theory of non-equilibrium phases of matter might eventually illuminate. We are not there yet, but the time crystal is a first, clean, precisely understood example of a non-equilibrium phase, and it opens the path. There are also more immediate, more concrete possibilities. Not free energy, we have closed that door permanently, and it is good that it is closed, but other things. Timekeeping. A time crystal, with its extraordinary rigidity, its habit of returning to precisely the same period even when the drive is imperfectly tuned, even when external perturbations nudge it, is in principle a very good clock. Not a clock that runs without any energy source because the drive must continue, but a clock that is exceptionally stable, whose period is locked in a way that ordinary oscillators cannot match. Ultra-precise timekeeping has applications in GPS, in telecommunications, in fundamental tests of physics. Whether time crystals will eventually find a role here is speculative and should be understood as such. But the rigidity is real, and rigidity is what clocks need. Quantum computing. Qubits are fragile. The whole enterprise of quantum computation rests on the ability to maintain quantum coherence, the delicate superposition of states long enough to compute with it. Decoherence is the enemy, constantly attacking, causing errors, reducing the quantum processor to a classical one before the computation is done. A time crystal phase might offer a way to encode and protect quantum information in the oscillating order itself, using the robustness of the phase against perturbations as a kind of natural error-correcting mechanism. This is speculative, but the physical intuition behind it is sound. If the system self-corrects toward its period-doubled state even when you perturb it, and if quantum information can be encoded in that periodic structure, you have a self-correcting quantum memory. The connections between time crystals and topological quantum error correction are an active area of theoretical interest. Sensing. The same sensitivity that makes a time crystal oscillate with extraordinary rigidity also means it responds in very clean, measurable ways to perturbations that break the symmetry. A well-designed time crystal sensor might detect tiny external fields or forces by the way they distort the subharmonic signal. Again, speculative. Again, not free energy, not perpetual motion, not magic, but real physical intuition grounded in what the experiments have established. These are the right speculations to have, the ones tied to the actual physics, not to headlines about free energy or infinite motion. And they illustrate something important. The value of a time crystal is not that it gives you something for nothing. The value is that it gives you something new, a kind of order, a kind of stability, a kind of periodic structure that doesn't exist in the equilibrium world, and that might turn out to be useful in ways we haven't fully imagined yet. But we are getting ahead of ourselves. Let's come back to where we are. 20 qubits humming in their refrigerated chamber, producing a signal at half the drive frequency, hundreds of drive cycles of self-correcting, period-doubled oscillation. A theoretical framework built over a decade, from Wilczek's 2012 question through Bruno's 2013 impossibility proof, through the 2015 no-go theorem of Watanabe and Oshikawa, through the rescue by Sasha and Else and Kamani and Nyack and Mersner and Sondi in 2015 and 2016, through Monroe's ytterbium ions and Lukin's nitrogen vacancy diamond in 2017, and finally to Sycamore in 2021 and the continuous time crystals of 2022. A whole decade of theoretical invention, experimental courage, and careful, painstaking verification. The question it all answers is one that a child could ask. Can something tick forever without running out of energy? And the answer, the beautiful, surprising, technically precise, honest answer, is yes. Under the right conditions. In a driven, non-equilibrium system protected by many body localization from the thermodynamic heat death that would otherwise consume it. Ticking not by consuming energy in the way a clock does, not by doing work, not by storing anything you could extract, but by existing in a phase where periodic oscillation is the lowest available mode of being, where time has, in a sense, a preferred rhythm, where the symmetry of mere moment-to-moment repetition is spontaneously broken, the way a crystal's atoms choose a preferred spacing, the way a magnet's spins choose a preferred direction. Not perpetual motion. Something stranger. Something that is permitted precisely because it is not doing what you thought it was doing, not burning, not running down, not exchanging anything with the universe in the ordinary energy economy sense. Just ticking. Just being. Phase crystalline order. Now not in the arrangement of atoms through space, but in the arrangement of moments through time. The universe found a loophole. And it is a beautiful loophole. Think about what that means for a moment. The second law of thermodynamics is one of the most fundamental and most stubbornly defended laws in all of science. Generations of brilliant people have tried to circumvent it. Maxwell's demon sorting molecules by speed, Szilard's thought experiments about information and entropy, every variant of every perpetual motion machine ever proposed, and every time without exception the second law has held. Entropy increases, disorder wins, the machine runs down, and yet here is a system that oscillates forever, that doesn't run down, that refuses to reach the featureless, information-free, maximum entropy state that the second law seems to demand. And the second law is not violated, not even slightly. The key is in what the time crystal is not doing. It is not extracting energy from nowhere. It is not decreasing the entropy of a closed system. It is not a machine in any meaningful thermodynamic sense. It is a phase, a configuration of matter that happens to be periodic in time, and that configuration is stable not because it is generating anything, but because it is frozen. Many-body localization is a kind of thermodynamic freezing. The energy that the drive puts in cannot flow, it cannot distribute, it cannot turn into heat. The system is not in equilibrium and never reaches equilibrium, and that is exactly what gives it the room to oscillate without dying. The loophole is not a trick. It is a new regime of physics, a regime where the rules of equilibrium thermodynamics genuinely do not fully apply, not because those rules are wrong in their domain, but because this system is outside that domain. In the non-equilibrium world, strange things are possible. Life is strange that way too, if you think about it. A living cell maintains its structure, its temperature, its oscillating chemical cycles for a lifetime, not by violating thermodynamics, but by being exquisitely, continuously non-equilibrium. The cell eats, the time crystal is driven. Both find their stability not in equilibrium, but in the careful management of non-equilibrium conditions. It is not an accident that the language physicists use for both is sometimes similar. And here is perhaps the most quietly astonishing thing about all of this. It was proposed in 2012 by a man who won his Nobel Prize for a completely different discovery in a completely different area of physics, who was simply asking a childlike question about symmetry. Who was sitting with the idea of a crystal, but the most ordinary solid thing, salt on your table, diamond in a ring, quartz in your watch, and asking, with the curiosity of someone who has thought deeply about the geometry of physics for decades, crystals repeat in space. Why shouldn't something repeat in time? It was declared impossible within a year, and then within 3 years of that it was proven to be possible. But only if you change the rules of the game. Only if you leave equilibrium behind. Only if you accept that the new physics isn't in the ground state Wilczek imagined, but in the driven, disordered, localized, non-equilibrium phase that a generation of younger physicists worked out in a flurry of papers between 2015 and 2017. And then in 2017, in 2 laboratories on opposite coasts it appeared, in chains of ions and in diamonds. And in 2021 it appeared again, more rigorously, more cleanly, with more theoretical armor, on 20 qubits inside a processor that had been built to run quantum algorithms. And in 2022, at room temperature, in light trapped in mirrors, we are at the beginning of understanding non-equilibrium phases of matter, not the end. The time crystal is the first member of a new family, not the last word on it. There will be other phases, other symmetries in time and in other more exotic dimensions of the state space that can be broken in non-equilibrium conditions. The theoretical landscape that opened up in those years between 2015 and 2022 is still being explored, and much of it is uncharted. But we have the first member, the one that ticks, the one that was dreamed up by a Nobel laureate asking a question about space and time, an analogy, the one that was killed and resurrected, the one that lives in ions and diamonds and superconducting qubits. The one that ticks without burning energy because it was never burning energy in the first place, It was just being, periodically, in time. There is something deeply calming about that if you let yourself feel it. You are, right now, lying somewhere, or sitting somewhere, or perhaps drifting on a train somewhere, surrounded by ordinary matter. The salt on your kitchen shelf, if you have one, is a crystal. Its atoms are locked in a regular lattice, repeating over and over in 3 dimensions, because that is the lowest energy configuration those atoms could find when they were cooling from solution. They didn't choose it. The physics chose it for them. Spontaneous symmetry breaking in space, happening all around you all the time, in every solid thing, in every grain of sugar, and every flake of iron, and every chip of quartz. And somewhere, in a laboratory cooled to 40 millikelvin, a collection of 20 superconducting qubits briefly managed something that those salt crystals cannot do, not just repeating in space, repeating in time. Ticking out a rhythm that the drive itself doesn't perfectly dictate. A rhythm that is theirs, the system's own preferred beat, stable, self-correcting, persistent across hundreds of cycles, pointing toward a theoretical forever. The universe spent about 14 billion years making the conditions possible for something like this to exist. The first generation of stars had to burn and scatter their heavy elements. The Earth had to cool and form solid ground, had to evolve and eventually produce a particular kind of curious primate who sat down and thought about symmetry for long enough to ask whether space and time might work the same way. Then that primate had to build quantum processors and dilution refrigerators and learn to program disorder into individual superconducting circuits. All of that so that matter could tick in time. I find that extraordinary. I hope you do too, wherever you are listening from tonight. I hope you have had your lamp on long enough to carry this far. Or perhaps you fell asleep somewhere in the middle, and that is just as well, because the physics will still be true when you wake up. The time crystal will still be ticking, theoretically, in its ideal form. The Sycamore processor will still have run its hundreds of drive cycles. The ytterbium ions will still have oscillated with period 2t when poked every t seconds. The nitrogen vacancy centers in Mikhail Lukin's diamond will still have hummed their million-spin chorus at half the drive frequency. We started tonight with a very simple image. Ordinary salt sitting on a shelf, its atoms repeating across space. And the question, why not in time? It seemed like a question with an obvious answer, because time is different from space, because the second law of thermodynamics won't permit it, because everything that moves runs down eventually, because there is no free lunch, not in physics, not anywhere. Those answers are right in their domain, but they are not complete, because outside that domain, in the driven, non-equilibrium, many-body localized wing of the universe's physics, the answer is different. Outside that domain, time has a crystal, not a perpetual motion machine, not a free energy source, not a clock that will run your city or a battery that never dies. Something simultaneously smaller than that and stranger than that. A phase of matter, a configuration of the world that is periodic in time, the way salt is periodic in space, a thing that ticks, not because it is burning something, but because ticking is what it is. Frank Wilczek asked the question in 2012. He was told it was impossible in 2013. By 2015, the theorists had found the real form of the answer. By 2017, the experimentalists had touched it. By 2021, it had been demonstrated on a quantum processor with a degree of rigor that made the theoretical predictions vivid and real. By 2022, it had been seen at room temperature, in light, in a condensate of cold atoms, oscillating inside a cavity of mirrors, choosing its own rhythm. The story is not finished. No good story is. But this chapter has an ending that is genuinely satisfying, which is the best kind. The truth outwonders the hype. It always does if you're patient enough to find it. You don't need a free energy machine to be astonished. You just need a system that can break time translation symmetry while obeying every conservation law perfectly. A system that can tick without running down, not because it has found a way to cheat the universe, but because the universe turns out to have a room in it where ticking forever for free in that specific and technically precise sense is simply what some matter does. That is strange enough. That is more than strange enough to carry into sleep. If you've enjoyed this slow walk through the physics of time crystals, through Wilczek's 2012 question, and the years of theory and experiment and quantum hardware that answered it, a like and a subscribe would mean a great deal to this channel. Small creators like me rely on your support to keep these journeys going, and if you found your way here looking for something to fall asleep to, I hope it served you well. And do let me know in the comments where you're listening from tonight, and what time it is in your corner of the world. I'm always grateful to know. Until next time, sleep well, fellow voyager. The next journey keeps until you wake.